Electronegativity is a measure of an atom's tendency to attract electrons in a covalent bond. A covalent bond is the sharing of valence electrons, and that's usually within nonmetals. So when you have atoms of the same element, you'll have an equal sharing. But if you have atoms of different elements, you're going to have an unequal sharing. That's what we're going to explore with this video. Electronegativity increases as you move up a column or to the right on a period of the periodic table. Fluorine is the most electronegative atom. The closer an element is to fluorine, the more electronegative it will be. Electronegativity is quantized. And what we have on this periodic table is showing those values that Linus Pauling derived. Now we're going to use these values, but you do not need to memorize them from me. They should be provided for you if you need them. On at least one of the labs that we do in most of my classes, you will need these values, and it should be provided within the lab write-up. Now, since electronegativity can be quantized, we can use the electronegativity difference between atoms to determine what type of bond will occur. Now, when we have some of these atoms, like our diatomic elements here, remember our upside down L, these are our diatomic elements. So the elements in their ground state exist as covalently bonded molecules. So we have H2, N2, O2, F2, Cl2, Br2, and I2. These are all gases in their elemental state. And because Dalton's atomic theory still holds, and we have two atoms of the same element, they have equal sharing because they have equal electronegativity. So that is the definition of a non-polar or a pure covalent bond. Now we have quantized these values, and because we've quantized these values, we actually will define that a nonpolar or a pure covalent bond is going to have an electronegativity difference. So the absolute value of the electronegativity difference that will be less than 0.4. We consider that a nonpolar bond. If the electronegativity difference is between 0.4 and 1.8, we call that a polar covalent bond. If it is greater than 1.8, then that is an ionic bond. And an ionic bond is an electrostatic attraction between a positively and negatively charged ion. So when we have a bond like the bond between carbon and oxygen, carbon's electronegativity is 2.5 and oxygen's is 3.5. So the absolute value of the difference between 2.5 and 3.5 is 1. So that lands squarely in the polar covalent bond. Now, when we show a polar covalent bond, we can draw what's called a dipole moment. And this dipole moment is simply an arrow that points to the more electronegative atom. We have this little crosshatch area here on the electropositive atom. For contrast, if I show you something like calcium and oxygen, the difference in electronegativity there, 1.0 for calcium and oxygen is 3.5. The absolute value of that difference is 2.5, and that lands us in the ionic territory. Now what I want to show you is CH specifically. Now in organic chemistry, we call CH a nonpolar bond. The electronegativity difference is exactly 0.4. Now 0.4 could put us in either spot because we do not have an equal sign here. In organic chemistry, we call that nonpolar because typically there's enough carbon-hydrogen bonds that they cancel one another out. And we'll talk canceling in a later video. In general chemistry, we will call this slightly polar, and we will draw a dipole moment. It won't be a big dipole moment, but there is a dipole moment that starts at hydrogen and points more towards carbon. Let's try some other bond types. So here we have nitrogen and carbon. Now nitrogen is closer to fluorine, so nitrogen should be more electronegative. The value we have on this table is 3.0. The electronegativity value for carbon is 2.5. Again, we're taking the absolute value. So the difference is 0.5. Now that leads us to a polar covalent bond. We can draw that dipole moment, again pointing towards the more electronegative atom. For the next one, we have sulfur and oxygen. Sulfur is down here, oxygen is here. Now you can see oxygen is more electronegative because of the value given, but you should know that since sulfur is removed from fluorine by one row and oxygen is right next door, oxygen is going to be more electronegative. So the difference between these electronegativity values is 1.0. This is polar, and the dipole moment starts at sulfur because it's the more electropositive, points towards oxygen, which is the more electronegative. For HCl, or hydrochloric acid, we have 2.1 for hydrogen. Here's hydrogen. And we have 3.0 for chlorine. So the absolute value of that difference is 0.9. That is also a polar covalent bond. And we point from hydrogen, which is electropositive, to the chlorine. Then we have hydrogen and fluorine. Hydrogen again is 2.1, fluorine is 4.0. So that puts us at 1.9, which is just over the threshold, so that is an ionic bond. We don't have a dipole moment for ionic bond because we have a discrete exchanging of electrons. Hydrogen simply gives up its electron to fluorine.